Hello, everybody, and welcome back to Pre-Calculus with Mr. Beck, where I've got your back and you've got your back. As we begin our day two of e-learning, I want to do a quick recap of where we've been. In 8.1, we solved right triangles, and then we began to apply them in more real-life situations. What we're going to be doing today is we're going to be solving more triangles, but we're going to ask ourselves what happens if they're not right triangles. The types of triangles that we are going to be solving today are going to take us back a trip down to geometry. I don't know if you guys remember angle, angle, side, and angle, side, angle. These are congruences. And when it comes to congruences, we know that if we have two angles and then the side, whether it's between or right next to them, of one triangle and another triangle, we know those two triangles end up being congruences. And we're going to use this as a frame of reference as we begin to say, if we have these kind of triangles, then we are going to be solving these triangles with the law of sines. We also have side-side angle. I don't know if you guys remember side-side angle is not a congruence. And the reason why it's not a congruence is there are multiple triangles that can result from that. We're going to explore that in video number 3. So for video number 1 that we're going to be working with today, we're going to be talking about kind of like where does this law of sines come from? And our law of sines can be seen in the following two formulas. Sine of angle A over A equals the sine of angle B over B, which equals the sine of angle C over C. Or we can reciprocate each of them to look like so. And I'll go through as we're solving to figure out which form of these two we want to work with. Now, what the law of sines says is if we take the sine, which if you remember, sine is actually a ratio. If we take that sine ratio over its opposite side, that's going to be equivalent to the sine ratio of another angle over its opposite side. Let me redraw that a little bit better. Okay, what does this mean and why do we care about it? Well, I don't know if you remember from geometry, if we have any triangle, the largest angle is opposite the largest side, and the smallest angle is opposite the smallest side. Take a moment to write that. So that's where those ratios kick in to say, okay, the ratio of any angle to its opposite side is always going to be equivalent in any triangle, which is really a cool idea if we think about it. Now, I'm going to begin this proof, or at least looking at these kind of triangles with a problem that we did last time in 8.1, where we said we had a spotlight that was at this corner, which I am going to call A, as in angle A is 45 degrees. And then we have a spotlight on the other side, which I'm going to call C, angle C. And that where those two angles met up on the cloud was at a point B. And what we cared about for that problem 8.1 was we said, okay, what is the height of that cloud cover? The reason why we cared about that, if you want to look at it in a math perspective, is that was our right angle. So we were finding a portion of the right angle. Now we're going to throw that H out of the way and we're going to say, maybe I want to know the length of the light beam here, or maybe I want to know the length of the light beam here. And I've matched those up with little a is opposite of angle A and little c is opposite of angle C, just so we could show the mathy aspect of this. So if you notice, it's very similar to the triangle I have over here. So I'm going to work with this triangle. Let's make this one the red triangle. And if I'm working with angle C here, I can say the sine of angle C is equivalent to its opposite. So the opposite is going to be the height of this triangle over the hypotenuse of this red triangle, which is A. So the sine of angle C equals H over A. And I am going to solve this for H, A times the sine of angle C. Now, if I take this half and this right triangle, and I'm working with angle A, I can say the sine of angle A is going to be equivalent to its opposite, which is H, over the hypotenuse of the blue, which is C, and I can solve that to say H equals C times sine of angle A. And let's go ahead, combine these two statements together. Since they are both equivalent to H, we can say that C times the sine of angle A is equivalent to A times the sine of angle C. Then if we divide both sides by AC, on the left, the C's are going to cancel, and on the right, the A's are going to cancel, and we are left with the expression sine of A over A equals sine of C over C, or the first and the third portion of the law of sines, which is kind of cool. It's a really quick proof, but it helps establish, we can figure out what's going on. We're kind of cheating by working through the height of the triangle. We're cheating to say, well, that's important. We're going to ignore it because we just care about the opposite sides and the opposite angles. So a lot of people at this point ask, well, what happens if this height, what happens if that height does not lie inside of the triangle, which is why we have the situation over here. Situation over here, let me go ahead and redraw that this is the red triangle. And in retrospect, I should have drawn everything so that that blue one was on the right and the red was on the left. Okay, and the red triangle actually, if we want to look at it as a right triangle, is going to be this one. So we can once again say the sine of angle C is the opposite H over A. In solving that, we get H equals A times the sine of C, which I saw over here as well. So let's bring the blue triangle back into play. Here's my blue triangle. And this time, I'm not actually going to find the sine of angle A because angle A is inside the triangle, but the blue triangle that I care about is outside of the triangle. So if you remember with the linear pair, that the angle that I'm going to be working with in the blue triangle is 180 degrees minus that A. So I will go ahead and write the sine of 180 minus A is its opposite over hypotenuse, H over C. And this, we're going to pause a moment to say, okay, I have a sine of 180 minus A. Well, the sine of 180 minus A should be equivalent to the sine of A, but let's actually go ahead and prove that. If you remember from 7.5, if we take the sine of one angle minus another angle, that's going to be equivalent to the sine of the first, cosine of the second, minus the cosine of the first, sine of the second, which if we bring it down to this problem, that means sine of 180 cosine of A minus cosine of 180 sine of A. And that equals H over C. And sine of 180 degrees is 0. Cosine of 180 degrees is -1. And I do show that now I have the positive sine of A is H over C. So what this means is it really doesn't matter what kind of triangle we have, whether it's an obtuse or an acute triangle, we know that the law of sines is actually going to work in all the different cases. So that's it for the overall proof ideas that we're going to be working with. We are now going to jump into the applications. I'm going to save that for video number 2. And the applications we're going to begin with are the two congruences, angle, angle, side, and angle, side, angle, followed by video 3, which is going to talk about the side, side angle, which is what's called the, I know this, it's what they call the, nothing like having a brain fart there, called the ambiguous case. I kept wanting to think ambivalous case. I'm like, no, the ambiguous case.